All right, so now this is part 2 of the push-forward pullback topic, which I really should call the pullback, push-forward, pullback, because we've already talked about pulling back functions, pushing forward vector fields, or vectors, not vector fields, but vectors, and then pulling back is what our subject today, pulling back one-form fields. We're going to pull back covector fields. And we're going to discuss the pullback of covector fields, and then we're going to talk about going to coordinates, right? We're going to talk about how this all works when you actually do have a chart mapping, a chart map U, and coordinate system on your manifold, which is a bit more of a specific condition. But if you do have those coordinates, then we can leave the coordinate-free discussion behind and stick with a coordinate discussion, which is a very practical way of doing it, because if you actually have these functions defined, you want to use this coordinate. If you have these functions defined, you almost certainly have them defined in a coordinate system. And the coordinate system gives us a basis to our tangent spaces and all of that. And we're going to see how that actually works. And then at the end, we're going to talk about expanding this pullback here to form fields of a tensor of rank 0 n, right? And then that'll be it. And then we should be able to get back to what we really want to do, which is understanding this interpretation. I'm in no rush. I mean, I want to make sure we go through this with a lot of detail. We get all these topics. Each one of these topics is worthy of understanding. So, okay, so let's begin and finish this up. So in the last lecture, we left off, we decided that we were doing everything coordinate-free, so this was kind of gone, and so were these chart maps. We had fully studied the push-forward for vector fields, the pullback for functions, and now we're going to study, I promised, the push-forward for, not vector fields, push-forward for vectors. That's important, actually. Right? When we talk about the push forward for vectors, we're talking about we go to any particular spot and we're going to push forward into the tangent space of the image point of that spot of the manifold. So if I'm at the manifold point X, the image of that point is 5X, and that point has a tangent space. Inside that tangent space lives a vector, which is the push forward of any vector, of a particular vector in the tangent space in Marshall at X. The reason that's important is because now we're going to talk about another space associated with Neal, right? And we're expecting a pullback on this space. And this is, we're going to call alpha. Alpha is going to be a dual vector or a covector field. So alpha is a covector field. So alpha takes a point in Neal. See, now I've gone to coordinates because I've got the V alpha there. So let me scratch that. It takes a point somewhere in Neal, say a point, I'll call it a point P in Neal. And once it has a point P in Neal, then alpha places a cotangent vector, or identifies a cotangent vector in the cotangent space at that point P. So the cotangent space, I guess, is T star at P of Neal, right? Alpha of Neal picks out one covector in that space. And a covector, of course, takes a vector and produces a real number. So if I get alpha of P, I should be able to take some vector in tangent space, say y at the point P, and this operation is a dual space mapping that gives me a real number. There, I just cleaned that up a bit, right? The alpha, the cotangent field on Neal, picks out a cotangent vector at P, which operates on a tangent vector at P to produce a real number, right? So that's ultimately what we're going to broker to exploit this to give us this mapping. So this, by the way, alpha is sometimes called a section of the cotangent bundle. When you start looking up, trying to figure out what the heck I'm saying here by Wikipediaing things, sometimes you'll see a section of the cotangent bundle. That's what alpha is. Alpha is a section of the cotangent bundle. And we can take a section of the cotangent bundle, or we can take, what's a much easier way of saying this, the way we've been using it, a cotangent field or a dual vector field, and we can pull it back into being into the space of sections of the cotangent bundle of Marshall. So we're going to pull this cotangent field from Neal back to Marshall. And it's forced upon us by this guy. I guess I could write this as lambda 1 on n and lambda 1 on m, right? What this represents the set of cotangent fields, right? Covering throughout the manifold. So that's sort of it would be called the fiber bundle of, it's the cotangent bundle in the language of fiber bundles. But I don't want to be distracted, and I don't want you to feel like you have to study fiber bundles to get this. You just have to study manifolds. So this is the set of cotangent fields on Neal and the set of cotangent fields on Marshall. Now notice it's different than this. Remember, this is the vector space at a point. So I can push forward the vector space at a point, but I can only pull back a whole field for cotangents, and we'll see why a little bit later. Let's see, it'd be pullback. So pullbacks have the stars up here. The pullback of alpha, right? And alpha has to act at the point x. So this is the pullback of alpha, so whatever this pullback, alpha is a field, right? So we pull back the entire field, but so the entire field operates everywhere, or in the range of this operation, but it has to be evaluated at x, right? So the pullback of the field, but evaluated at x, and then operating on a vector x that's a member of the tangent space at x, a member of the tangent space at x, right? That has to equal the original alpha, but evaluated at phi of x, at the image point of x, operating on the push forward of x, which we've called in our world, in our notation, psi of x, or located at the point x, the push forward of the vector x. Notice the functions are gone now. We don't need these functions anymore because this map acting on this vector is a real number. This map acting on this vector is a real number. Okay, so the original vector field, which is alpha, evaluated at the image point of x, operating on the push forward of a vector from the original tangent space at x, right? You push forward, you end up with a vector in the tangent space at psi of x, right? That's what this guy is. If you take some cotangent field, evaluate it at psi of x, and execute this operation, you better get the same answer as the pullback of alpha into the cotangent fields on Marshall, operating on that original vector, right? There's really only one way to do this, right? And this is it. So this direction now is established to be a pullback of the cotangent field. So far we can pull back cotangent fields, right? We can pull back cotangent fields, and we can push forward specific vectors from a single tangent space forward, right? We can do this for any tangent space, but we don't need a vector field to push forward. We can push forward individual vectors. Notice that it's hard to think of it the other way, right? If you took an individual point, right, and a cotangent vector from that individual point. Let me see, I'm worried about me being wrong here, but let me think. If you took an individual point here and you pulled it back to to the domain. You took a point in the image, you pulled it back to the spot in the range, and well, it seems like that should work. I'm trying to think about why does this need to be a field, right? Here we just took a vector in a tangent space X, and we got a vector in the tangent space of the image of X. Why don't I just take a covector in the cotangent space? And I think the answer must be regarding this function. Just because we have this function does not mean we have this function, right? So if I picked a vector in the cotangent space of some point here, some point y, right? For example, up here's a point y. If I picked a vector in the cotangent space of y, right, at y, I would need to find the corresponding point over here. I would need to take the inverse, right? And I can't do that because I can't be guaranteed this thing is invertible like that. So because of that, I'm forced to take an entire cotangent field, right? And I can pull back the whole field because now I don't need an inverse function. I just need the entire space of Marshall, right? So now I take the field, I pull the field back, and then after I pull the field back, then I decide what point to deal with over here. Now that pulled back field can operate on any tangent space in Marshall, right? Because it's a whole field. It's a whole field on Marshall. This pullback field is pulled back to the entire space of Marshall. So then I pick a particular place, identify it, and then push forward the vector, and that's the reason. So that must be the reason. The reason is we don't have guarantees knowledge of the inverse function. So when we do this pullback operation, we're pulling back an entire cotangent field. Okay, so these are the three core definitions. Let me clean this one up a little bit. All right, so there's our two pullbacks and one push forward. All right, so now we've done this completely coordinate free. So now we're going to lay down coordinates on Marshall and Neal and come up with some formulas for these things. All right, so now we look at our situation, and we're going to go into select charts, right? That's what the way books often say it is. We go to some chart, or we affirm some chart. So we'll affirm a chart U over here, and then a chart V over here. And once we say that, we're talking about coordinates now. So now this function up here, psi, is actually going to be understood as psi. I'll give it a little hat, mu, and then x now is actually the coordinates of x. So I might throw up an alpha up there just to indicate it's the coordinates of x. So this is now available to us, right? We now know the muth coordinate. Given the coordinates of a point in Marshall, I can get the muth coordinate of the corresponding point in Neal, and I have as many possibilities for mu as I have the dimensionality of Neal, all right? So that's what it means by, and in the literature when you read, we go to coordinates. We go to a coordinate system. So now none of this was in a coordinate system, so we kind of got to rethink this in terms of coordinates. So let's just do it one by one. The first one's actually quite easy, right? Because we just replace this with phi hat. F now isn't a function on Neal. F is now a function on the coordinates. We have access to that, right? We have access to, it's F is a function of y. Well, not of y. F is now a function of the coordinates y. So I guess I would write y beta maybe, right? F is a function of the coordinates of y. And psi is now psi hat of mu, which is a function of the coordinates of x. So we're just looking at f of psi hat 0 of x alpha psi hat. I'm writing psi. I mean phi each time I say this. Phi 1 of x alpha. And notice this is kind of a tricky way of writing things, right? Because There's only one function f, so that's good. But f has as many slots as the dimensionality of Neal, right? But each of these slots of Neal comes from a phi hat, right? So the phi hat 0 slot, what I really mean is x0, x1, x2, dot, 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 all the way up to xm minus 1, where m is the dimensionality of Marshall, right, little m. So sometimes I write x alpha in there as though to mean all of these slots together, right? But then in this case, I broke up the mu's into their own slots. So I guess you could write, if you wanted to be really shorthand and sketchy, you could write f hat mu of x alpha, right? Where you mean all the mu's and all the alphas, right? But either way, all I'm saying is these things are now functions of the coordinates up here. So this is pretty easy. And phi hat of f is really, the pullback of f is this function here, because alpha is the domain, or x alpha is the domain. The coordinates on Marshall is the domain. So this one is just composition. It's just function composition, and it's really easy to understand. All right, let me erase this and do the next one. Oops, I just noticed I lost my continuity with Wikipedia. So Wikipedia calls the coordinates on U, on the chart U, they call it little u. So that would be little u alpha. And the coordinates on chart V are called little v beta, right? I've been calling it y and x, right? That's not consistent with the Wikipedia article, which I'm trying to stick with. I'm showing this formula essentially in the Wikipedia article. Okay, so the first thing to think about here now is that once we have a coordinate system on U and on V, on these two charts, we now have access to the coordinate bases for the tangent space. So in the tangent space, I'm going to write the basis. I'm going to actually put the basis in there. So I'll give myself a little bit of room, and I will go partial U alpha. That's the basis for the tangent space at x of m. And likewise, we can do the same for the tangent space over here. We call this tangent space as basis partial v. I'll give it a beta, not that that matters much. So now we have a basis for the tangent space, and that's automatic. Once you have a coordinate system, you can always have a coordinate basis, and it's these nice differential operators, which was consistent with our definitions of things and how differential operators work. Now, given that everything is linear, if I can tell you what the push forward is of a basis vector, then I can tell you the push forward of any vector, right? So if I know the push forward of the basis system, I know the push forward of every vector possible in this tangent space. And so the rule goes like this. So here's the definition. The push forward of the basis vector, the coordinate basis vector, is equal to the, I better lower this down so you can see the definition of, it's this partial derivative, right? This partial derivative here, the partial derivative of our function between the manifolds, which is a function of u, so it's this partial derivative with respect to the variables u, and Einstein summed over the basis vectors in this vector space, right? This is the definition of how you push forward a basis vector. It's really, really simple. You're basically taking the partial derivatives of this transfer function. I'll call it the transfer function. It is a transfer function, right? But obviously that's a word used in engineering control theory, the transfer function. But I'm looking for a word for this function. So the transfer function is what I'll call it. And nobody's going to confuse this with engineering control, automatic control systems theory. So this function here, you just take these partial derivatives and you sum over the basis vectors, and each of these basis vectors maps into the basis system of this vector space. And once I can do this, right, then any vector x, right, which is by definition equal to x alpha partial u alpha, right, by linearity, I just have to map this part and I'm good. So this is the definition. Now the question is I've just sort of claimed it was the definition. We should check to make sure it fits our, this isn't the definition. I just said this is how these basis vectors transform. Let's check to make sure that that actually works. So what I'll do is I will write down the definition like this, right? So here we have, this is a basis vector, right, which is a vector. So this is a vector. We'll call this vector x, right? This is a vector in the tangent space at the point x. And it is operating on the pullback, right? This is the vector here, and I'm using this piece of the definition. The vector operating on the pullback of a function that exists in Neal. So this is the function. This is the pullback. This is the definition of the pullback. So here's our vector operating on the pullback of a function. Does it equal the this set of derivatives times simply the basis vector? Oh, I'm missing a little b here. Basis vector derivative on f. So we got to evaluate this left-hand side. So we just use the chain rule, right? So this derivative is going to equal the derivative of f with respect to each of these slotted variables, which is phi hat mu of, I don't know why I put an x there, right? That's not right. I should have put a v, right? And it should be, say, v, I don't know, vb. So this is vb. The derivative of f with respect to that times the derivative of phi hat mu vb with respect to vb. I guess this should be a dummy variable. It shouldn't even be a v. Hold on, let me clean this up. Okay, first of all, it's not v, right? The coordinate system here is u. So I messed that up a moment ago. So the transfer functions are functions of u, and in order to get my indices right, I got to call the transfer function index b. So to take this derivative, we first take the derivative with respect to the independent variable inside, and that's this thing, right? But that is effectively the same as this, right? Because you're basically taking f is a function of v, right? Well, v is now being replaced by this composed function. So this guy here actually equals vb, right? That's the same derivative. It's going to be the exact same derivative. And then this, of course, is the chain rule, right? Where this is now a function of u, and so we're executing the derivative of a composite function using the chain rule. And so this side here does in fact equal that side there. So this definition works just fine. And this is how you push forward vectors in when you have coordinates available to you. All right, so can we do the same for pulling back? All right, so this formula here will yield the push forward of a basis vector in the cotangent space, or the cotangent bundle, or the section. Basically, what I'm saying is here, alpha, which is the form field on Neal, is just dv alpha, right? So I pick one particular basis vector, the alpha basis vector, and that's just going to be my form field. And I'm interested in how that pulls back, right? I'm interested in the pullback of the basis form field like this. And that's what this is. This is the pullback of the basis form field, but evaluated, the pullback is then evaluated at x in principle. But the pullback, the definition of this pullback as a field, in fact, I probably have this wrong, right? The pullback of the field itself is going to be defined we're going to use this as our formula for it. And I'm just going to prove to you that this formula works, and that'll be the next step. But this is the formula. So the pullback of the basis form field is this set of partial derivatives times the basis vectors or basis form fields in Marshall, which is the du, right? So I take the partial derivatives of the transfer function, and I just use the alpha transfer function, right? So if I'm interested, you know what? In fact, I probably should use the letter I, because alpha kind of always means sort of standing for them all. But I is like a fixed value. I want the ith, the ith basis vectors pullback, right? So I go to the ith of the transfer function, the ith coordinate transfer function, right? This is the transfer function that's associated with that coordinate, right? It's so the ith value of the ith formula will produce the ith coordinate of a point located at u alpha. So I get all the coordinates in Marshall of a point x, and those coordinates are called u alpha. And then I go to the ith transfer function, and it'll give me the v-ith coordinate in Neal, right? So I'm only interested in that one if I'm interested in this basis vector. So I is fixed, right? I is fixed. And then this formula, I take this Einstein sum. My B's are kind of weird, aren't they? Let me make this beta. So it's the Einstein sum of these partial derivatives, the partial derivatives of the ith transfer function with respect to the Marshall beta coordinate, and I sum them all up, and I end up with this sum expression that represents the cotangent field in Marshall that corresponds to the pullback of the basis vector cotangent field in Neal. So does this definition fit our property that we depend on? That the property being that the pullback of the cotangent field from Neal in Marshall operating on a vector in Marshall at the point x should be the cotangent field in Neal operating on the push forward at x of that same vector, right? So let's do that. Let's look at let's try to calculate this thing. Let's calculate this side right here. We'll calculate this part first. And what we're interested in is our alpha, the alpha field. You know, my alpha there. Let's make it a little bigger so it actually looks like the field as opposed to a subscript. It was kind of looking like a subscript. If we set alpha to be dvi, right, then we use this formula to calculate the thing in parentheses here. So this formula ends up this way, and I have alpha here. So I guess if I'm going to use this formula literally, then I should change my little alpha there to an I, right? Because that's what sort of tags which of these basis vectors I'm actually doing. So this is the pullback of the ith basis vector in the cotangent space of Neal. That's what this is. So then I take it and I operate it on an arbitrary vector in some tangent space x, right? So that means this has to be evaluated at x, which basically means this partial derivative is calculated and then evaluated at x, right? And this guy lives in the tangent space of x, right? This guy lives in the tangent space of x. And this is the coordinate expansion of an arbitrary vector in the tangent space of x, right? It's just the components and the vector. So then I can combine these using the dual space mapping, right? So I'm taking this cotangent vector in the cotangent space at x now, and I operate on this vector, right, which by the nature of the dual space mapping is going to give me this delta function, right? Delta B and gamma. And so processing this, that alpha now should be an I, right? So processing through, we end up with this delta function turns the gammas and the betas into the same thing. So now I end up with this expression, right? The components of the vector times these partial derivatives of the transfer function. And that alpha, again, is an I because it's referring to the ith basis vector. That's how we track that we're using the ith basis vector, is it shows up because we're taking partial derivatives of the ith component transfer function. So we end up with this thing here. Well, does that equal this, right? Does that equal the other side of this expression, right? Well, let's see. I think I can calculate the other side of the expression, right? How do I do that? Well, let's see. I take the vector, right? What do I need? I need the push forward of the vector x. So here's the vector in Marshall's tangent space, and I push forward, and using our push forward formula for the basis vectors, I know that each basis vector in Marshall pushes forward with this formula. So everything's linear, so I'm now pushing this forward, and x gamma, which I guess I should have my little bars all over this thing, right? X gamma is just a bunch of constants. So, but this part pushes forward, and that push forward comes through this formula right here, right? And now, so that's the push forward part. Now I have to operate on the original cotangent field in Neal, which was just dvi. So this dvi, oops, I still have that alpha, which I want to be an I, right? So by dvi, when you operate on dvi, what happens? Well, the dvi operates on the delta, the partial of v delta, and that gives you a delta function. The delta function will be I delta, and so the only thing left, so this delta will become an I, this will go away, and you'll be left with, basically, just to be clear, I'm forming dvi partial dv delta, right? That's the dual space mapping, and that's what equals this delta function. And when I do that, the indexes clean up. This delta function turns the deltas into i's. That delta there becomes an I. This becomes this thing, which equals, well, being equal to the delta function, it equals the delta function. So when I execute the delta function, when I execute the delta function, it goes away, and it just leaves this behind. But this here is the same as that, right? The only difference is the dummy variables I choose were gamma over here, and it ends up being b over here. So these things are the same. This is met, and therefore this is actually the coordinate way. Once we have coordinates, that is how you form the pullback with coordinates. Good. Okay, so there's only one last thing to talk about before this lecture's over, and that is how do we broker this to, this is just one forms. This is just the pullback of one forms. How do we broker this for the pullback of two forms or three forms? I shouldn't even say forms. I should say the pullback of tensor fields of one forms. They don't have to be two forms or three forms. Remember, two forms, three forms, whenever we say two form or three form, we're talking about anti-symmetric tensors, right? But we can also just have, tensors of the dual space that are not anti-symmetric, and we can pull all of these back, any one of these forms or not. And let's quickly cover the obvious. It's a very straightforward extension of this to do those pullbacks. So here we have the definition, right? This is the pullback of a one form operating on a vector in Marshall is equal to the one form operating on the push forward of the same vector, right? So clearly alpha is a one form because this is a vector, a single vector in Neal, right? This is a single vector in Neal, and this side is a real number. This is a single vector in Marshall, so this must be a one form on Marshall. So what about two forms or three form, or what about higher order tensors of the cotangent space, right? And the answer is really, really straightforward and simple. Let's say this was no longer, let's say alpha was actually an element of V star tensor product, V asterisk tensor product, V asterisk, right? So it's a 0,3 tensor, right? Let's say alpha is a 0,3 tensor. Notice I'm not saying alpha is a 3 form, although a 3 form is a 0,3 tensor, right? So I'm taking care of all of these at once. Well, if it's a 0,3 tensor, then I need 3 vectors, right? So what would I end up with? I would end up with a formula that's very straightforward. We just do this. The pullback, got to do my stars right. The pullback of alpha evaluated at x, operating on the vector x, the vector y, and the vector z, right, would equal the original 0,3 tensor evaluated, which has still got to be a field. You still have that problem. But it's simply the push forward of x, the push forward of y, and the push forward of z, right? So it's just a very straightforward expansion of, once you can do it for once you can do this for a rank 0, 1 tensor, you can do it for any rank tensor just by expanding the definition like this. And the exact same thing would be true for push forwards as well, for tensor spaces of V, tensor product V, tensor product V. All right? Okay, so that covers everything we need to know. We will use this definition in the proof that we're trying to get up to, right? When I pointed this out back here, right? Where was it? This, we are push forwarding. We are going to do a push forward on the metric, which is a 0,2 tensor. We're going to push forward on that metric. I'm sorry, we're going to do a pullback on that metric. And it's a 0,2 tensor, but it's going to be a very straightforward application of what we just did. Okay, so I think now we are actually ready to get started with the actual proof, and we'll begin that, or with the actual demonstration of how to interpret R, and hopefully we'll get started with that in